Hello students, this video is just a reminder about polynomial division because our next video we're going to be dealing with asymptotes and you have to use polynomial division to find asymptotes. So there are two ways to divide polynomials. The standard way is called polynomial long division, but there's a shortcut called synthetic division, and to show you how that works I'm going to take an example, x cubed minus 2x plus 1, and divide it by x minus 2. But we're going to do this both ways. First, we're going to do polynomial long division, and then I'm going to show you synthetic division, and you can see how the two methods line up, and you'll be able to see that synthetic division is much quicker. It's a nice little shortcut that's going to save us a lot of time. So let me zoom in here. To divide this using polynomial long division, first, we're going to set up our long division bracket. Our divisor goes on the outside, and our polynomial goes on the inside. Make sure you have every term represented. So we have an x cubed minus 2x. Notice we skipped over the x squared, so I'm going to put a plus 0x squared. That's just so I don't forget that it's there. And then minus 2x plus 1. So it goes in order from x cubed, x squared, x, and then a constant term. The first step is we have to figure out what to multiply x by in order to turn it into an x cubed. To turn x into x cubed, you would have to multiply by x squared. So that goes on the top. Then we take the x squared and we multiply it by the divisor x minus 2. That's going to give us x cubed minus 2x squared. But since we're dividing, we subtract this, so we're going to turn our x cubed negative and our 2x squared positive. On our next line, we combine all of our like terms. Our x cubed and our negative x cubed, these cancel each other out. Our 0x squared and our plus 2x squared combine to give us a positive 2x squared. And our negative 2x and our positive 1 don't have anything they need to combine with. So we're just going to carry those down. Now we start over. We ask the same question, but this time we're looking at the 2x squared. So we ask, what do I multiply by x to turn it into a 2x squared? Well, it would have to be a positive 2x. So now we take that positive 2x and we multiply it by our divisor, x minus 2, and we write the result on the next line. So that would be 2x squared minus 4x. But we're subtracting, so we have to flip both of our signs, and then we combine like terms for the next level. Negative 2x squared and positive 2x squared, these cancel each other out. Negative 2x and positive 4x add together to give us a positive 2x. And then we have a plus 1 that we carry down that doesn't combine with anything. Now we start over and we ask, what do I multiply by x to be 2x? What would I multiply by x to get 2x? And that would be positive 2. So now we take that positive 2, we multiply it by our divisor, and we write the result on the next line. So 2x minus 4, but we're subtracting, so we flip both signs, and that gives us some terms we can combine. 2x and minus 2x combine and cancel. Plus 1 and plus 4 combine to give us a positive 5. Now we would start over, but notice that our new line has a lower degree than our divisor. So if we were to ask the question, what do I multiply by x to turn it into a 5? Well, you can't multiply by x by anything to turn it into a 5. So this is where we stop, and we refer to 5 as our remainder. So our answer would be x squared plus 2x plus 2, remainder 5. This right here is our answer. That was a long and tedious process. Fortunately, we do not have to continue like this. We're about to talk about a shortcut, synthetic division. So synthetic division is magic. You don't really need to know why it works or how we figured it out, but it's a shortcut that's going to get us to our answer way faster. So here's how it works. We take this number, -2, and we change its sign, and we write that first. So if that's a -2, we make it positive. If it was a positive number, we would make it negative. Then you're going to draw a division bracket, but upside down, and it needs to be a little longer than you're used to. Then we take the coefficient of each of these numbers. So the coefficient here would be 1, 0, -2, 1. And we write them 1, 0, -2, 1. And that's how we set it up. Notice that all of the x's have sort of disappeared. These are just internal to the way synthetic division works. So here's the process. We are going to add 1 with the number that's below it, but there's nothing there. So we just carry the 1 down. Then we're going to multiply 2 times 1, and that goes in this space, like up and to the right. So 2 times 1 gives us 2. That goes right here in this space. Then we're going to add 0 plus 2. That gives us 2. Then we're going to multiply 2 times 2, which gives us 4, and that goes here. Now we're going to add -2 plus 4, which gives us +2, and multiply the +2 that we just wrote down times our divisor 2, and that gives us 4 again. That goes here. And now we're going to finally add the 1 plus 4. That gives us 5. And we are done. But you might be thinking, how is this our answer? Well, it's a little tricky. Sorry, I erased our 4 here. So our answer is 1, 2, 2, 5, but we actually have to write that in a way that resembles what our answer should really look like. So whatever you got on the furthest right, that's your remainder. The number before that is our constant, so +2. The number before that is our x term, and the number before that is our x squared term, so 1x squared. So we end up with 1x squared plus 2x plus 2, remainder 5, which is exactly what we ended up with before. But this is a shortcut that will save us some time. So the moral of the story is, inside our division bracket here, we are going to be adding columns, and then outside we're going to be multiplying our divisor. Now, after a few more examples, this will hopefully become a little bit easier. Let's do an example from the homework common version. Question 21 from homework 10A common asks us to complete the synthetic division table. So I do want to point out there should be a bracket here, but I think just formatting, they probably weren't able to write in a bracket, which makes it a little bit difficult to figure out like what all of these boxes are supposed to be. So I will rewrite this. They want us to complete a synthetic division table for this division problem. So here's how we set it up. We look at what we're dividing by, our divisor, and we flip the sign of the number. So instead of a -1, we're going to write a +1 on the outside. And then I'm going to draw my bracket, make it nice and big, and inside my bracket along the top row, we're going to list all of our coefficients. So we've got a +9, and then that was for our y to the 4th term. Then we have a y cubed, that's -13. Then we have a y squared, that's coefficient 1. And then we have a plus 3y, that's coefficient 3. And notice that there's no constant term. It's not like plus 3y plus 7. We don't have a constant term, so we have to actually write a 0. So you need all of your terms represented. Now it's time to divide. So first, we start by adding 9 plus whatever's below it, which is nothing, so we carry the 9 down. Now we multiply 1 times 9, which gives us 9. Now we add negative 13 plus 9. That'll give us negative 4. Now we multiply 1 times negative 4. Now we add 1 plus negative 4, which will be negative 3. Now we multiply 1 times negative 3. Now we add 3 plus negative 3. Now we multiply 1 times 0. Now we add 0 plus 0, and we're done. These are weird problems. So check out where all my numbers are spaced. We have to figure out how to fill in our chart up at the top here. So they've got their divisor here is the same as our divisor here. And then they've got the 9 and the 9 already filled in. That's here and here. And notice the space in between. We have that space too. It's just theirs is really tiny, so it's hard to see. But then in the next row, they've got negative 13, and there's a blank where we need to put in the 9 and the negative 4. Then they've got a 1 and a blank for negative 4 and negative 3. Then they have a blank, that's for a 3, a negative 3, and then a 0, which they already have. And then 0, 0, 0 should be the last row. Okay, so what does our answer represent? All of these numbers down here at the bottom, this is our answer. We start with the number on the far right. That's our remainder 0. Then the number before that is a constant, so plus 0. Before that is our x term. Before that is x squared, and before that is x cubed. And I just realized that I got all of these wrong because we weren't working with x, we were working with y. So these should be y cubed, my bad, y squared, and y. So the point of doing this for this particular question is because they asked us if y minus 1 is a divisor of our polynomial. Well, if something is a divisor, that means that when you divide, you don't get a remainder. So if you end up with a remainder 0, the answer is yes, this is a divisor. You get a nice, neat answer with no remainder when you divide. So the answer is yes. The next synthetic division problem in the homework common version is actually the next problem, question 22. All we have to do in this problem is complete the synthetic division table. They don't ask us any other questions. But this one's going to get a little crazy. You can see some of our numbers here, like negative 212. Yikes. So let's set up our bracket. We start with our divisor, and we flip the sign of this number. So instead of a positive 2, we write a negative 2 on the outside of the bracket. And now I'm going to draw a big bracket, and we're going to fill in our coefficients. So we start with 5t to the 5th. We put a 5 here. Then we have negative 2t to the 4th. Then we have positive 3t cubed. Then notice there's no t squared term. We skip over that. So I have to put a 0t squared, and then a negative 2t. And again, there's no constant term. So I have to put a 0 for my constant term. Okay, it's time to divide. First, we add 5 to the number below it, but there's nothing there, so we'll just carry that 5 down. Now we multiply negative 2 times 5, and that goes here. Now we add negative 2 plus negative 10. Now we multiply negative 2 times negative 12. That'll be positive 24. Now we add 27. Now we multiply negative 54. Now we add. Now we multiply Now we add. Now we multiply. Now we add. Okay, so when you're multiplying, you're kind of going in this direction. And when you add, you're kind of going in this direction, so down. So I know I did that one kind of fast, but it was our third example. I figure you've got the hang of it by now. Let's figure out how to fill in our boxes here. So they've got the -2 on the outside, and they have their 5 over their 5. So the next boxes they need us to fill in are the -2, -10, and they have the -12. Then we do 3, 24, 27, then 0, -54, -54, then -2, 108, 106, and then they have the 0, -12, -12. So they're just basically asking you to do the synthetic division on your own, fill in what they left blank, and you're good to go. This synthetic division is going to save us so much time when we have to divide things later on. So real quick, this felt like magic. Why in the world does this work? Well, the reason I wanted to do polynomial long division and synthetic division earlier on the same problem was so that we could see the parallels. So every time in polynomial long division that we do a step in the problem, we end up doing this stage where we have to subtract or flip our signs. Excuse me. Synthetic division takes care of that by the fact that it changes the sign of this number. So every time we multiply, instead of getting multiplying by a -2, we're multiplying by a +2, and that'll change the sign of everything for us. So we don't have to do the step here where we're changing the signs every time. It cuts out that step, so that's convenient. And then also, you can basically trace where your numbers are coming from. So I'm going to use color coding here. This 2 comes from here. Sorry, let me do that one more time. This 2 comes from here. This 4 comes from here, and this 4 comes from here. So it's sort of combining the multiplication and the addition into a single step. And ultimately, we end up with the same exact answer because of the fact that we started with the opposite sign, and they just cut through all of these steps where we first multiply and then add. Here's our multiplication going this way, and then here's our addition going this way. It's just a very shortened, quick version. But you can kind of see where all the numbers belong in the polynomial long division, but with synthetic, you're going to save a lot of time. All right, so there's one more topic we want to discuss in this video, and it is the polynomial remainder theorem. This is a nice little math trick that will help you figure out if something is a factor of a polynomial. So as you can see with all of our work with division, it can be kind of tough to figure out if something is a perfect factor of a long, nasty polynomial, because you'd have to divide, and then you have to see if there's a remainder, and that can take a while, even with our shortcut, even with synthetic division. So this polynomial remainder theorem can save us some time. If something is a factor of f of x, let's do it this way. The polynomial remainder theorem says if we divide a polynomial by x minus a, then the remainder of our division is going to be f of a. So we could plug a into f and see what the remainder would be before we ever even divide. Now that's not super useful in algebra, but what is useful is something called the factor theorem. So if we take the polynomial remainder theorem and we kind of extend it out logically, if x minus a is a factor of our polynomial, that would mean there would be no remainder. That's what it means to be a factor of something. When you divide it, you don't get a remainder. So what we're really concerned with is whether we have a remainder or not, whether our remainder is 0 or not. Well, if f of a is the remainder and f of a equals 0, that means there's no remainder because our remainder would be 0. So our factor theorem is going to help us a lot with questions about whether something is a factor. So here's how it works. If you see a question that says, is blank a factor of your polynomial? So let's say we have, is x minus 4 a factor of x cubed plus 2x minus 3. All you have to do is take this, flip the sign, and plug it into f. Then that'll give us 4 cubed plus 2 times 4 minus 3, which is 64 plus 8 minus 3, which is definitely not 0. So this is our remainder, right? What would that be? 72 minus 3 is 69. So 69 would be our remainder. That's what the polynomial remainder theorem says. If it's 0, if our remainder is 0, then that would mean that x minus 4 is a factor. But since our remainder was not 0, it means that it was not a factor. So that's it. We're plugging this point in, we're seeing if it's 0. If it's not 0, it's not a factor. If it is 0, it is a factor. So question 23, once we know that, can be a relatively quick problem. So we're going to look to see if these 5 things are factors of p of x. To do this, we're going to first see what f of negative 4 is. Remember, you have to flip the sign. So when we're checking x plus 4, we're going to be testing f of negative 4. And then to test x minus 4, we're going to plug in f of 4. Then to test x, think of that as an x plus 0, we're going to test f of 0. Then to test x minus 1, we're going to check f of 1. And finally, x minus 2, we're going to test f of 2. So we're going to plug all of these things into p. P, darn it, not f. I do this all the time. All right, so bear with me for 1 second. We're going to be plugging and chugging into a calculator because nobody in their right minds would want to do this by hand. So I'm plugging this in. Okay, so I've just typed my function in, and now I'm going to plug in all of my test points. So first I'm going to plug in negative 4. And I get 0. Well, that was convenient. When I plug in 4, I get negative 2,880. When I plug in 0, I get negative 32. When I plug in 1, I get 0. And when I plug in 2, I get 0. So the remainder is the value we just found. We found the remainder when we divide. If the remainder is 0, then that is a factor. So x plus 4 is a factor. X minus 1 is a factor, and x minus 2 is a factor. For the other pieces, the other binomials, or monomials, we ended up with a remainder when we tried to divide, so to speak, so that those are not going to be factors. So this is a shortcut that can save us a lot of time as long as you don't mind plugging and chugging in a calculator. That was actually the last question of this video. I accidentally had an old question on this document. So we are done. I hope that helps you on your homework.